So part C asks, find the limit as x approaches 2 of g of x over x squared minus 2x. Okay, so to evaluate this limit, we need to be able to find g of 2. Since this x goes to 2, and again, this is a two-sided limit, we need to find g of 2 so we can try to evaluate this limit. And to find g of 2, we need to use this area function, this one right here, and we're going to use that to calculate the value of g of 2. So that's going to be found by finding the area between the bounds 0 and 2. So I'm just going to write this down more formally. So g of 2 is going to be equal to the area from 0 to 2 of f of t dt. Okay, and 0 and 2 represent those two green dots that I've drawn in there. And when I evaluate that, I'm finding the area underneath that curve. So it's going to have this area here, and I'm going to have an equivalent area under the curve from 1 to 2. Okay, so the net area in this case is going to end up being equal to 0. So g of 2 is equal to 0. Now, what that allows me to do then is allows me to evaluate this limit. So the limit as x approaches 2 from both sides of g of x, so this would be g of x over x squared minus 2x. That's going to be equal to 0 in the numerator, and when I plug in 2 into the denominator, I end up with 0 divided by 0. Okay, the nice thing about this is it fits the condition for L'Hopital's rule. So we're going to use L'Hopital's rule for this problem. So once I've established that I have 0 over 0, because f is a continuous function, f is continuous, that means then that g is also smooth and continuous or differentiable. So g is differentiable. Okay, well that means I can apply L'Hopital's rule because I have the condition 0 divided by 0, g is differentiable. So applying L'Hopital's then, I'm going to end up with the limit as x approaches 2 of g prime of x over 2x minus 2. And then I'm going to evaluate this limit. So I need g prime of 2. So I'm going to go to my g prime. So that's the same as f of 2. And I'll write that down. G prime at 2 is equal to f at 2. When I take a look at f at 2, we get a value of 4. So this is equal to 4. Okay, so then that means that g prime at 2 is equal to 4. In the denominator, when we plug 2 in, we end up with 4 minus 2, which is equal to 2. So that's going to be negative 4. Okay, and then that is then the limit of g of x over x squared minus 2x as x approaches 2. So the limit is equal to negative 2. Part D says the average rate of change of g on the interval from negative 4 to positive 2. Okay, find the average rate of change. So the average rate of change of g is going to be the g of 2, so the endpoint, minus g of negative 4, and that's all over the interval 2 minus -4. So this would be the slope formula, which is the average rate of change or the average slope of g. And so we need to establish g of 2. Okay, looking at up above, we've already figured out g of 2 is equal to 0. So I'm going to plug that in. 0 minus, we still need to find g of -4, and that's going to be over 6. Okay, so this is working out g of -4. G of -4 is going to be the area under the integral starting at 0 to -4 of f dt. Okay, so now it's important that we recognize that I am integrating in this direction. So any area under the curve is going to be opposite. So going to my area function here, we are going to integrate in this direction. The area pieces that I calculate when I do that, maybe I'll just do this in a slightly different color to differentiate it. Okay, I'm going to use green here. So the area under the curve here, this area in here is a trapezoid. Okay, so that's going to be 4 plus 6 divided by 2 is 5 times 2, so that's going to be an area of 10. This area over here is going to be a triangle, so 2 times 6 divided by 2 is going to be 6. So that area is equal to 16. Okay, so that's 16 units squared. But because I'm going backwards, the area above that curve, the x-axis, is going to be negative. So when I work that out, g of -4, that's going to be that area, which is -16. Okay, so that's going to be the value of g of -4. So I can plug that into my slope formula, -16, and working that out, I end up with 16 over 6, which simplifies to 8 over 3. So that is the average rate of change of g on that interval. The second part of this question says, does the mean value theorem guarantee a value c between -4 and 2, which g prime c is equal to the average rate of change? Yes, it does, because since g is continuous, so f is continuous, so I'm going to write this over here, f is continuous, therefore g is smooth and continuous. So we need to establish this condition first. Once we establish a condition of smooth and continuous, then we can apply the mean value theorem. So by MVT, we know that g of c must exist, and it must be for g of 2 minus g of 4 over 2 minus -4, which is equal to that. And by the mean value theorem, we know that c must exist between 2 and -4. Okay, and so we can apply the mean value theorem as long as we state the condition that it is smooth and continuous based on the fact that the derivative f is continuous.